Welcome to CivilizationX. We can ignite fusion in the lab. We still cannot run a power plant on it. That gap is the story. The anomaly is simple. A kilogram of fusion fuel can equal about 10 million kilograms of coal in energy output. Yet civilization still burns fuel by the shipload and fights wars over supply. Global primary energy demand is still about 620 exajoules a year. That is hospitals, factories, desalination, transport, and data centers moving matter and information every second. When fuel is mined, shipped, and priced through geopolitics, a blackout is never just a blackout. It becomes a clinic on diesel, a kitchen in the dark, a workday that depends on the next fuel spike. In December 2022, the National Ignition Facility crossed a line people had talked around for decades. The fusion reaction produced more energy than the laser energy delivered to the target. Not a power plant, not a grid, but a real scientific gain. And now the race is no longer just about physics. It is about control, materials, and whether AI can help manage systems too unstable for human reflexes alone. The question here is mechanical, not mystical. How do you turn light nuclei into heat, heat into confinement, and confinement into electricity without the machine destroying itself? That is where the sun's logic collides with Earth's limits. Fusion is the opposite of combustion. You do not burn fuel with oxygen. You force light nuclei, usually deuterium and tritium, so close together that the strong nuclear force wins over their electrical repulsion. A tiny loss of mass becomes energy. That is why 1 kilogram of fusion fuel can equal about 10 million kilograms of coal. But the fuel has to be hotter than 100 million degrees Celsius. And at that temperature, no wall survives contact. So, engineers use two paths. NIF crushes a capsule for an instant with lasers. Tokamaks like ITER and ST40 hold plasma in magnetic fields. Here is the strange part. The reaction itself is not the hardest thing. The hard part is keeping plasma dense, hot, and stable long enough for useful gain. Plasma is a restless, charged fluid. It kinks, wobbles, and disrupts in milliseconds. That is why AI matters. Not as a robot operator, but as a control system. Google DeepMind and Commonwealth Fusion Systems are using reinforcement learning and evolutionary search to optimize plasma control and speed spark design. The US Department of Energy's Stell Foundry project is using AI to design stellarators with models that can do in milliseconds what now takes hours or days. And at ITER, Alberto Luarte says AI is already being used to build high-fidelity digital twins of plasma behavior and engineering systems. Meanwhile, private fusion is no longer a fringe bet. Tokamak Energy's ST40 reached 1 million amperes of plasma current and a triple product of about 8 plus or minus 2 times 10 to the 18th meter cubed times kilo electron volt times seconds, the highest ever in a privately owned tokamak. Global private investment has now exceeded $10 billion, with $4.48 billion raised in the year to July 2026. That money is chasing the same bottlenecks: neutron-resistant materials, steady-state operation, extreme heat exhaust. The real milestone is not fusion works. It is that fusion has moved from theory into contested engineering. In December 2022, NIF showed scientific net gain from the target. ITER is in machine assembly in France, aiming for experiments in 2034 and deuterium-tritium operations in 2039. But a lab result is not a plant. ITER is designed for 500 megawatts of fusion power, and its cost is over 22 billion euros. The unresolved gap is durability. No reactor has yet proven it can survive neutron damage, manage continuous heat, breed enough tritium, and make electricity cheap enough to compete. If the economics tighten and the control systems keep improving, fusion could become a major grid source later this century. Some projections put it at up to 50% of global electricity by 2100 in a low capital cost scenario, with trillions added to GDP. But that path depends on whether AI-guided control, new materials, and pilot plants can survive real operating conditions first. The constraint is real. The data exists. Whether the systems built around it can act on it at scale, that is the next engineering problem. Stay with CivilizationX.